Hello everyone, this is lecture 14, linear regressions. So in this lecture, we're going to develop basic concept of linear regressions from a probabilistic framework. And later on, we're going to estimate something called correlations, coefficients, and then use that to interpret the results that we get from calculate the coefficients and from what we have in the problem. So first, let's talk about regression. So this is the technique used for the modeling and analysis of numerical data. So it's kind of the idea of an empirical model that we just have data and you don't have any particular functions to deal with. We have to somehow fit the data using some model, right? And we can use regressions to do that as well. And we're going to exploit the relationship between two or more variables so that we can gain information about at least one of them through knowing the values of the other. Okay. Regressions can be used for predictions, estimations, hypothesis testing, and modeling causal relationship between the variables. Most of the time, what we do, probably the most basic model regressions that we're going to look at is the linear regression. So it's going to be very similar to the least square criterion that we looked at a few lectures ago. So for the linear regressions, I want to model the dependent variable capital Y in terms of three predictors, capital X1, X2, and X3 in the form of Y equal to F of X1, X2, and X3. And of course, typically we'll not have enough data to try and directly estimate the function f. We're just going to approximate, right? Try to fit the curve into the set of data points that we have. And therefore, usually we have to assume that it has some restrictions form, right? And the restriction form that we're going to look at is going to be in terms of the linear form, right? Because y now going to depend linearly on x1, x2, and x3. So the terminology that we would like to know here is that capital Y is called the dependent variable and X are the independent variables, right? So in this case, this is dependent variable. And this three variable is called independent variable. Right. Another name for dependent variable is called the outcome variable or response variable. So outcome variable, or there's another name is called response variable. And there's also other names for independent variables. It's called predictor variable or explanatory values. Predictor variables or explanatory. Be careful here. So explanatory values. All right. So we're gonna use this type of models to write down functions to fit into the data, right? Because we're working with linear functions. So the linear function is going to have the form AX equal to B. Right? So a linear probabilistic model, so studying variables that are deterministically related to one another or discretely related to one another. So predict the value in a way, predict the value of a dependent or response variable from the values of at least one explanatory or independent variable. So if you remember the least square criterion, so we want to make predictions on the outcome, right, using the parameters that we do the estimate on using the data that we have. That's the idea for the linear probabilistic model. So we want, in other words, we interested in understanding the relationship between variables related to the non-deterministic fashions. In a way, we want to estimate or calculate the number called the correlations coefficients. And that process is called the correlations analysis. Right, so you want to somehow measure the strength of the correlations between two variables. So that's the idea for the linear regressions, right? So we want to predict the value of the dependent variable based on the value of independent variables, right? And we want to interpret this relationship between dependent and independent variable through the calculations of the correlation coefficients, right? Because we want to know how strong or what is the strain of the correlation between dependent variables and independent variables. Now moving on to the relationship between the linear regressions and the data set that we have. So there are different types of relationships that we have. So the first two pictures that you see here is called the linear relationships because you can fit a linear line into this data set, right? So either you can have the data set that moving into increasing from left to right, or you have data set that going down from left to right, right? So it depends on the data set. We can have a different type of lines, right? The line with positive slope or the line with negative slope. In addition to that, we can have the nonlinear relationships between the data set and the curve that we try to fit. And we have seen this type of relationships already in the previous problems when we fit in, when we use exponential functions or logistic functions to fit into certain data. Now, there's certain strong relationship between the data set and or the data point and the linear or the curve that you want to fit. Because the data points kind of cluster around the line that you want to fit or the curve that you want to fit. When this happens, you say that the relationship between the data point and the curve are strong, right? There's also the case where you have weak relationships, right? Where the data points kind of spread out and move away from the curve that or a little bit further away from the curve that you want to fit in, right? So that kind of relationships called the weak relationships. And also there are certain times it's called no relationships at all, right? Even though you have a horizontal line going through this kind of data set, but the idea of the linear regressions or the least square criterion is that you want to fit the linear curve, which is either going up or going down and not gonna be a horizontal line, right? So in that particular case, we have no relationship between the data points and the curve that you want to fit. Now, moving on to the definitions of a linear probabilistic model, right? Again, it's very similar to what we have seen in linear, the least square criterion, right? So we looking to fit a curve or linear line into the set of data points, right? And the linear lines, of course, is equal to, is y equal to ax equal to b. For A is the slope and B is the y-intercept, right? And we already spent time and derived the formula for the slope in the intercept using the least square criterion. I'm not going to rewrite those particular formulas here. We can actually go back to previous lectures to look at the formula when we actually deal with the problem or the example later in this lecture. Okay, so for a linear probabilistic model, there exists parameters A and B such that for any fixed value of the independent variable x, the dependent variable is related to x through the model equations. You have y equal to ax plus b plus an epsilon, right? So epsilon in this case called the error term. That's not going to be our focus in this lecture. We're just going to focus on the linear part of the equation, which is ax plus b. Right, again, here, a is the slope, b is the y-intercept, and epsilon is the error term. Of course, x is the independent variable, and y is the dependent variable. All right, so now let's take a look at the following pictures, try to depict the equations that we just wrote down. All right, so you have a bunch of data points, which is the points in blue, right? So the points in blue is going to have x, x sub I, y sub I. So that's the data point that's going to be from the data sets that you got. Now, you want to fit a linear line through this point, right, using the linear regressions. And the line is going to be y equal to ax plus b plus epsilon. Now, for convenient, for later derivations, I'm going to use different notations than I have used over here. Instead of just y, I'm going to use y hat. Right, so it's going to be useful for me later on when I do derivations. All right, so y hat is going to be the line that you want to fit into this data set. All right, here this is the point from the data set that you got, and this is the point from the estimations or the linear regressions that you model. And the difference here is called the error term, right? So that is the error. Okay. Here, x value is the predictor, and the y value is called the observed value. Okay. Sorry. So this is the x value. This is the observed value. This is called the predicted value. Sorry. So this is predicted value. Because you want to make the predictions using the linear line. Right. And this part of the graph is called the y-intercept. And here you can use the relationship between the horizontal part and the vertical calculations to calculate the slope of the line. Right, so the slope is equal to A and the y-intercept is equal to B. Okay, so again, to calculate or to approximate, estimate the value of A and the value of B, we're going to use the formula that we have derived in the lecture notes related to the least square criterion. Okay, now what we're going to do is we're going to derive a number is called the regression sum of squares, right? So before that, I'm gonna write down a few notes here. The variations of the y values around their own mean. So the mean is the average value. So this variation is going to be the sum of y minus y bar, right, which is the mean square, right? For the mean is equal to 1 over n times the sum of y. So it's just the average of the number of data points that we have. So in this case, I call y bar to be mean value or average value. Okay. The next formula that I'm going to write down is the variations of y values around the regression line. So it's the sum of y minus y hat square. So for y hat is the regression line. So this is the regression line. All right. Now the regression sum of square is equal to the sum of y hat minus y bar square. So that is the difference between the regression line and the mean value. Okay, so let's take a look at the following graph. Right. So in this graph, we have a few things here. We have the line, the regression line that we want to fit into the data set, right? We have the mean value of the predictor, of the predicted value. And we have the y value from the data set that you observed, right? So the difference between, or the variations between the data set and the line, or the regression line, is going to be y minus y bar, y hat square, sorry. And now this is going to be, this part is going to be the sum of, right, so this is y hat, right, minus y bar square. Now between this point and the mean is going to be the sum of y minus y bar square. Okay, and from this analysis, from this picture, we can see that the sum of y minus y bar square is equal to the sum of y minus y hat square plus the sum of y hat minus y bar square. All right, so from this picture, we're going to write that. So we have the sum of y minus y bar square, right? So y minus y bar square is equal to the sum of y minus y hat square plus the sum of y hat minus y bar square. All right. Now, what we're going to do is we're going to divide both sides for this particular term. You get 1 equal to the sum of y minus y hat square over the sum of y minus y bar square plus the sum of y hat minus y bar square divided by the sum of y minus y bar square. Next, we're going to move this term to, actually, we're going to move this term to the left-hand side so that we get, so I'm going to rearrange something here. So I get the sum of y hat minus y bar square over the sum of y minus y bar square equal to 1 minus the sum of y minus y hat square over the sum of y minus y bar square. Okay. And this particular formula is called the coefficients of determinations. I'm going to write down the explanation for that a little bit later. And for this model, right, we set this right-hand side, or this, to be equal to R squared. This is called the coefficients of determinations. Right. For the coefficients of determinations, it is a statistical measure. Right. Statistical in regressions model that determines the proportion of variance in the dependent variable. That can be explained by the independent variable. That can be explained by the independent variable. In other words, for sure, the intuitive idea of the coefficient of determination is that the coefficient of determinations tells how well the data fits the model. Nations tells how well the data fits the model. All right. From here, you can actually derive another coefficient. It's called the correlations coefficients. The derivations is rather lengthy, so I'm gonna skip the derivations and just give you the formula for the correlations coefficients right here. And we're going to use this to estimate the relationship or to look for an explanation or the strength of the linear relationship between two variables, and in this case, the dependent variable and the independent variable. Okay, so you have R to be equal to this particular equation. There are certain explanations for R in this lecture. So R can be a positive number, R can be a negative number. Or basically R is between -1 and a +1. When R is greater than 0 is positive, the regression line has positive slope. When R is less than 0, the regression line has negative slope. Right. When R equal to 1 or R equal to -1, all the data points lie exactly on the regression line. Right. All the data points lie exactly on the regression line. It's probably impossible for that to occur in real life, but that mathematically is that how you define R equal to 1 and R equal to -1. So if it's close to positive or -1, then all the data are close to the line. If it is close to +1 or -1, then all the data are close to the line. Or if, in other words, if R is close to positive or -1, then you have that the data point is close to the line. When R is not close to positive or -1, that means all the data are not going to be close to the regression line. the fit in that case not going to be a good one. So all the data points are not close to the regression line. So in this case, the fit is not a good one. Right. So the general rule of thumb is that a value of absolute value of R less than 0.8 indicate a poor fit of data to the regression line. So a value of absolute value of R less than 0.8 indicates a poor fit of the data to the regression line. All right, so here is the geometric explanation for the different values of R. So in this pictures, right, all the data point fit exactly on the line and is going down. So this is the case of R equal to -1. In this pictures, all the points lined up exactly on the regression line and the line is moving up. This is the case where you have a positive slope or R equal to 1 in this case. So here the points kind of cluster around the line, and the line is going down. So this is going to be R is not close to R is not close to -1. So even this cluster is kind of moving away from the line. In this case, you can see it's more clear that all the data points spread out and stay a little bit far away from the regression line. So R is not close to +1. +1 because the line is going is increasing. So in this case, this is R is equal to 0. So we say that no linear relationship. All right. So that's the idea of the value of R, the correlations coefficients. And so again, the correlations coefficients, even though we already write down the information earlier, the correlations coefficients measure the strength of a linear relationship between two variables. Right. So what we're going to do in the next couple of examples is that we're going to calculate using the data. We're going to estimate the value of the slope and the value of the y-intercept. And then we calculate the value, the correlations coefficient to see what is the strain of a linear relationship between independent variable and dependent variables. So let's move on to the example. All right, so let's start with the first example. So in this example, suppose an appliance store conducts a 5-month experiment to determine the effect of advertising on sales revenue and obtain the following results. So here's the table of information that we need to look at, right? So this is gonna be in 5 months, and this is the month. And in this column, we have advertising expenditure, and the last column is the sales revenue, right? So what we're gonna do in part A is to find the sample regression line, right? And to find this regression line, we're going to use the formula that we obtained from the least square criterion. Again, the regression line is the line of the form y equal to ax plus b, for a is the slope and b is the y-intercept. Okay. So here is the Excel spreadsheet. What we're gonna do is in the first column, I have the advertising expenditure, and the second column is the sale revenue. Okay. What I'm gonna do again is to use the formula we got from the least square criterion lecture, which is in lecture 7. So let me open lecture 7. So this is the lecture 7, and this is the two formula that we're going to use to estimate, to calculate the slope and the y-intercept of the regression line. All right, so what we need is the product x times y. So this is going to be equal to 1 times or x times y. I'm going to track the formula down. So let me center this xy. The next one we need is x squared. So I'm going to type x2. Right, so this is equal to x times itself. I'm going to track the formula down. Right. And eventually I'm going to have to calculate something called y square, because let me go back to the problem here, right? So in the first part, I have find the sample regression line. The second one is to predict the sale revenue in if the appliance store spend $4.5 thousand for advertising in a month. And the last equation is that to calculate the coefficients correlations. And the coefficient correlations has the value of y squared, or the sum of y squared in the formula. So what I'm going to do next is to calculate y squared, and I'll put in this particular column. So this is y times itself. I'm going to track the formula down. Okay, so let me go back to lecture 7 again. So for A and B, we need the summation of x, y, the summation of y, the summation of x, y, the summation of x squared, right? So I'm gonna calculate the summations for all of this column. I'm gonna get sum of all of this entry. I'm gonna get that 15. I'm gonna track the formula to the right, and it helped me calculate the summation for each column. Now here, I'm gonna calculate A. All right, so A, which is the slope, is equal to, now let's type in the information for the numerator. So N now is 5, so you have 5 data points times the summation of xy minus the sum of x times the sum of y. So that's the numerator. Now divided by the denominator, which is 5 times the sum of x squared minus the summation of x altogether square. Now close the parentheses to end the denominator. Here we obtain the slope with the value of 0.7, right? So the line's going to go up. Now you're going to calculate the y-intercept, right? So again, the formula is type in the numerator. So the summation of x squared times the summations of y minus the summation of x times y times the summation of x. Now divided by the denominator is 5 times the summation of x squared minus the summation of x altogether square. And that is the information that we got for the y-intercept. Now, let me go back to the notes to write out this information. All right, so for part A, using Excel, we can obtain a simple regression line as follows. So regression line. This is going to be y equal to 0.7x minus 0.1. So 0.7 is the is the slope, and negative 0.1 is the y-intercept. Now we're going to use this model to predict the sale revenue if the appliance store spend $4.5 thousand for advertising in a month. So what we're going to do is we're going to calculate y given x equal to 4.5. So y is going to be 0.7 times 4.5 minus 0.1. Now, so if you do the calculations correctly, we're going to have this going to be 3.05, and this is in sale revenue, so 3.05, $10,000. Okay. Now, the next calculations we need to do is to calculate the coefficients of correlations. Again, here the coefficients of correlation is a measure to a measurement to measure the strain between the independent variable and the dependent variable. So here C is going to be here we calculate R, the value of R. So let me move to this part of the lecture, zoom in a little bit here. So I want to calculate the value of R, right? So we have the numerator is a little bit easy to type in. The denominator is a little bit harder, so I'm going to break down into two different parts, the numerator and the denominator. Right? So the numerator, is equal to n, which is 5 times the summation of x times y minus the summation of x times the summation of y. Okay, so that's the numerator. And for the denominator, right, so the denominator is equal to square root. Right, so the functions for square root in Excel is SQRT. So I open the parentheses. So I want these two terms, right, under the square root. So SQRT, square root of, right, so let me type in the first part under the square root. So 5 times the summation of x squared minus the summation of x altogether square, close parentheses. So that's the first part. And so that is just this term. Multiply with the second term here, right, which is 5 times the summation of y squared minus the summation of y altogether square, close parentheses for the second part of the denominator. And then I close another parenthesis to close the square root. So this is what I got for the denominator. Now the value of R, our calculation, is equal to the numerator divided by the denominator. All right, so R, the value of R is equal to 0.904. Let's just round it up to 3 decimal places. All right, so the conclusion there is that there are strong connections between the between the dependent variable and the independent variable. All right, go back to our problem here. So that means that so let me write down the value of R. So R is equal to 0.904. So there we conclude that there is a strong connection between the advertising expenditure and the sale revenue, between the advertising expenditure and the sale revenue. All right, so that's how you incorporate the informations of the coefficients of correlation coefficients. All right, similarly, we're going to move on to the next example, where again, we're going to calculate or find the sample regression line, and we're going to calculate the coefficients of correlations and see what's going to happen. So here, We have the data on the per capita gross domestic product and GDP of Mexico from 2000 to 2014. You have to set the table of data right here. I'm going to use this table of data to find the best fit linear model for the data. And then we're going to use the model to predict the per capita GDP in Mexico in 2016. Then later on, we're going to find the correlations coefficients for the data and see if the regression line a good fit to the data set or not. All right. So here, I'm going to turn into example 2. Right. So this is the data from the table we have here. Right. There are, let's see, so 1, 2, 3, 3, 4, 5, 6, 7, 8. So there are 8 data points. Gonna do the same calculation as the previous example. That is in this column, I'm gonna calculate x times y. This is equal to this time this. I'm gonna drag down the formula. The next column is x squared. This is equal to x times itself. Gonna drag the formula down. And y squared, right? Because later on we need to calculate the correlations coefficient and y squared in the formula. This is equal to y times itself. Drag the formula down. Now you need to calculate the sum for each of these columns. All right, so the summations of this, close the parenthesis, we have the sum, and we're going to drag the formula to the right. So it's help us calculate the summation for all of the other columns. Now you need to next calculate the slope of the linear model, like the slope and the y-intercept. Now let me turn to lecture 7 one more time. So for A, it's going to be equal to, so we're going to type in the information for the numerator. So n in this case equal to 8 times the summation of x times y minus the summation of x times the summation of y, close the parenthesis, divided by the denominator, in this case 8, times the summation of x squared minus the summation of x altogether squared. And this is the information that we got for the slope. Again, this is increasing a line, right, because the slope is positive. Next, we're going to calculate the value of the y-intercept. So it is equal to, let's type in the numerator. So the summation of x squared times the summations of y minus the summations of x times y times the summation of x divided by the denominator, which is 8 times the summation of x squared minus the summations of x altogether squared. Close the parentheses, and this is what we got for the y-intercept. All right, so let me go back to the note one more time. And in this case, in part A, you obtain that y is equal to 0.321 x plus 8.75. Okay. Let me stay consistent with the number of decimal places. So let's just route this into 2 decimal places. So 0.32. So 0.32 x plus 8.75. So that's the model that best fit into this data set. Okay. Now we're going to use this model to make a prediction for the per capita GDP in Mexico in 2016. All right, so that is x going to be equal to, so you start at 0, right, for 2000, and you end at for 2014, which is equal to 14. So in 2016, the value of x is going to be 16. All right, so y is equal to 0.32 times 16 plus 8.75. I'm gonna put this into a calculator and see what happened. So let me do a quick calculation here on the Excel spreadsheet. So this is equal to 1.32 times 16 plus 8.75, and we're gonna get 13.87 and in thousand. Right. Okay. So let's actually double check this information in the real data, okay? Right, so with a quick Google search, we find out that the per capita GDP of Mexico in 2016 is actually 8,875 US dollars. From the model that we come up with, we estimate that the per capita GDP of Mexico in 2016 is $13,870. It's a little bit, I mean, it's a little bit off, right? But still is a model that we can use to make some predictions in the future. I mean, in this case, we already have the information, but of course we can use this model to make further predictions for, let's say, 2024 or 2026 or something like that. All right, so let's find the next part is to find the correlations coefficients for the data and see how well the curve fit into the data set that we have. Okay, let me turn back to the Excel spreadsheet. Right, so here, again, similar to the last example, what I'm gonna do is I'm gonna put in the numerator and the denominator separately. Then later on, I'm just gonna use the number and divide one another. So the numerator of R is going to be A times the summation of X times Y. Let me use the equal sign. So A times the summation of X times Y minus the summation of X times the summation of Y. And this is what we get for the numerator. And for the denominator, it's gonna be equal to the square root. So SQRT, open parentheses, and then I'm gonna type in the first part of the formula of the denominator. Right? So 8 times the summation of x squared minus the summation of x altogether square times the second part of the denominator is n. So 8 times, so 8 times the summation of y squared minus the summations of y altogether square. Close parentheses for the second part of the term under the square root, and then close the square root. So this is what we get for the denominator. Now for R is equal to the numerator divided by the denominator. And we get 0.98, so which is really good for the curve to fit into the data set that we got. So let me go to part C here. For R is equal to 0.982. Right, let's round it up to 3 decimal places. And part D, right, so as R is close to 1, the fit is fairly good, right? So as R is close to 1, the fit is a fairly good one. Right. So that is the original point lie nearly along a straight line. Okay, so that's it for this lecture. Right? So in this lecture, we kind of revisit the idea of least square criterion, but we add one extra formula, that is correlation coefficient, to see the connection, the strong connection between, to determine if there is a strong connection between dependent variable and independent variable, or in other words, is there a good fit of the model into the given data? Okay, so that's it for me. Please let me know if you have any questions. Thank you.